welcome guys. Welcome to my introduction to the computational complexity theory. So this is my own notes of what I learned about computational complexity theory. So just for fun, but I make some highlights for this code language. So let us just work sentence by sentence. Okay, so before I start, please subscribe to my channel. Okay, so one can define a code language. So basically, if you have a complexity class, let's say this curly L, then one can define this code L to be a decision problem. Basically, the negation of this L inside this curly L. So for example, is for the N, so NP means that one can efficiently certify whether X belongs to L, right? So this is the non-deterministic polynomial time. Basically, if you have a problem L and you have some X, right, which is an input, then you can quickly check that whether L of X is true. Okay, so co-NP means that one can efficiently certify that L of X is false. So basically, you can easily check that whether X belongs to negation of L. Okay, so I think this is a definition. Its definition is clear, right? Because one can, so basically you can easily say, oh, this is no, then it means it's co-NP. So you can use the only polynomial time to say that, oh, this is not the correct answer. That means this problem is in a co-NP. Okay, so one important is that onset is co-NP, right? Because the set is NP, so onset is co-NP. So the idea is that if some language belongs to a set, then you can call both sides. So you can use CO both sides. So and then you get the results. So basically, this is just the logic results. So one theorem, a very trivial theorem, is that P is equals to co-P. This is trivial because if you can solve this problem in polynomial time, then definitely you can solve. You can easily get the answer. If someone gives you the X, then you can easily work in the polynomial time. So co-P is the same as P because you can solve in the problem in P. Also, exponential time, right? Co-exponential time is the same as exponential time because the same as the reason as P because you can solve the problem in the exponential time, right? So whether NP or P is not whether NP or co-NP is not different, has no difference here. Okay, so theorem. So you see, if XP is co-XP, right? So the next step we want to prove that the co-NP is the subset of exponential XP. Okay, so if L belongs to co-NP, right, and then we take co both sides, so we take a negation both sides, then we get the L negation of L belongs to NP. Right, but we also know that NP is a subset of XP. Sorry, so L negation of XP. So L bar belongs to negation of XP. So which you take a co both sides, you get L belongs to XP. So you prove that if L belongs to co-NP, then L belongs to XP. Okay. So the possible diagram is that co-NP and co-NP both containing P. Okay, some fact. So theorems, we collect some fact. Okay, so the first fact is that P basically is the subset of co-NP. So we want to prove. This is very easy, right? Suppose L belongs to P, and then we take co both sides, then we get negation of L belongs to P because co-P is the same as P, and then we take we know that P is a subset of NP, right? So L negation of L belongs to NP. Then L belongs to co-NP. We take co both sides. Okay. And the theorem say that if P is equal to NP, then NP is equal to co-NP. Now this is trivial because if P equals to NP, then co-P will equal to co-NP, right? But co-P equal to P, so NP will equal to co-NP. So this is a special case that if about the polynomial hierarchy. Okay, so we will talk about polynomial hierarchy maybe in the other lecture. Okay, so theorem, if NP equals to co-NP, then the onsets, that's if onsets belongs to NP. Okay, so this is somehow a little bit we need to illustrate. So the first direction is trivial, since that if onset belongs to column, we know onset belongs to column P. So, and we assume that NP equals to column P, right? So, then onset will be NP. So, this will prove this, okay? And conversely, we want to show that conversely is that we assume that onset belongs to NP, and we want to prove NP equals to column P. So, let's assume that L belongs to column P. We start from L belongs to column P. Then it will implies L bar, negation of L belongs to NP. And then we know that the set is NP complete. So there's a polynomial time reduction from set to L negation. Then we take a code both sides. We get L is L can be polynomial time reduction from the onset, right? So if onset belongs to NP, then NP equals column P. Okay, so let's see the final page. So the final page is that if L is defined to be column P complete, means that for each L prime in column P, there's a polynomial time reduction from L to L prime. Okay, so theorem onset is column P complete and trivial. So if L belongs to column P, we want to show that L equals to column P, then L can be polynomial time reduction from onset, right? So L belongs to column P, then negation of L belongs to NP. But all NP problem can be polynomial time reduction from set. So L negation of L from set. Then take code both sides. You get L is polynomial time reduction from onset. So you prove that the onset is called NP complete. So there's an interesting class. Some interesting class of problems say that NP intersection column P. So since we don't know whether NP is the same as column P, right? So this is just the possible diagram. So if one can, as I said, if one can show that P equals to NP, then NP will be same as the column P. Okay, so there are three problems that we will talk. Okay, so the first one is perfect matching. So perfect matching is column P, followed by bipartite graph. And the reason is that this is just my own note. So there's a okay. So maybe let's go to this page. I think. Okay, so for a perfect matching means that maybe let me just type the perfect matching. Hopefully, okay. So perfect matching means that if we focus on bipartite graph, somebody give a bipartite graph, then you can each vertices, right? You pick up some edge, you pick up some edge subset of the graph, and every vertex is exactly connected one of the edge. Okay, and then there's a thing called the Hall's condition. This is not easy to prove. Okay, but I may give a proof in some cases in the future. Okay, so given a set A, NA is a set of neighbors of A. Then the Hall's condition that if you give a bipartite graph, which is the left side is U and Y, right side is V, and the middle is H, has a perfect matching if and only if the number of the set of neighbor larger than A, for all subset A belongs to U. Okay. Okay, so this proves that the perfect matching belongs to so first one, the perfect matching belongs to NP, right? This is easy to check because if you want to check it. But by the Hall's condition that the perfect matching also belongs to co-NP. The reason is that if I give you a G which has no perfect matching, then you just need to check whether that means that you have some subset. You just need to check that whether a neighborhood A has the number of neighborhood A is less than A. So if there's no perfect matching, then you just need to check this. So you only need the polynomial time to check whether there's a you just need the polynomial time to check whether this is correct, have perfect matching or not. Okay, so this is an interesting result. Okay, so perfect matching actually is the co-NP and NP intersection due to Hall's theorem. And the second thing is that linear programming is actually co-NP, and in I think it's 1991 that one can prove that linear programming in P. Okay, so next thing, maybe in the next video I will give a proof that so determine whether a number is prime. Okay, determine whether a number is prime. We call it primes. So primes is a problem sets that this is this task basically gives you a number and you check whether this is prime or not. So if 2 is prime, 3 is prime, 5 is prime, 7 is prime, 11 is prime. Okay, so actually prime belongs to co-NP, and this is trivial, right? Because if somebody give you a certificate, then you just division. So you just divided that number. So division is a trivial algorithm. So it's also easy algorithm. So it's obviously that the price belongs to column P. And actually, there's a famous result I think in the 21 centuries that the actual price is in P. Okay, so next video I will give I will give a proof that the actual price in also in NP, and this is so-called Petty's theorem, I think. Okay, so this is my short video of introducing some easy proof of the code language, and also some discussion. Okay, and I will see you guys in the next video. Be sure to subscribe to my channel. Thanks.